right, let's do this. We've been spending our time talking about scatter plots and linear regression, and almost all the examples that you've gotten, a line was an appropriate model to model the data and then to use to make predictions. Any nonlinear data that we talked about, all we did was say, well, let's look at a residual plot and show that it's nonlinear. And this is an example of some data that's going to be not linear. And we're going to figure out in this section, what do we do about it? How do we fit a model to it and be able to make predictions? In this case, X is, I believe, length of the heart or length of the heart chamber for certain animals, you know, from a mouse all the way up to a big animal. And Y is the weight of the heart. In the real world, we would expect this to follow what's called a power model, because basically lengths are one-dimensional and weights or masses depend on all three dimensions. And so it's kind of like one of them would be, you know, X, and the other one would be X cubed. That's just a broad idea there. So we're going to look at the data specifically and see if that's the right model. So let's just start by looking at the data. I've got it entered into my calculator, and I've generated a graph. Now, these first couple dots are all jammed in at the left edge of my graph, but you can tell that a line is definitely not the right idea here. So let's start by just getting a linear regression equation and seeing what it looks like. So I go stat. By the way, my values are entered into list 3 and list 4. We'll talk about 5 and 6 later. So my x's are in 3 and my y's are in 4. If I want to do linear regression, I'm going to choose option 8, and I'm going to use list 3, comma, list 4. And I'm going to go ahead and put a comma and go to vars and get my y1 to go ahead and put it into y1 so we can put a line through the graph. So here is our regression information. We have an equation, and we have a correlation. So I'm going to list the info. The equation is negative 572.6 plus 242.8x. And our R value, the correlation. And then this brings up an interesting point. The correlation is 0.945. In this obviously nonlinear data, the correlation is still 0.94, which shows it's pretty strong. What you'll notice, if you have a small set of curved data, the line will still be fairly close to most of your dots, and that closeness to the dots is what factors into correlation. So even though it's obviously nonlinear, the linear correlation still is fairly high. All right, so we've got two options here. When your dots curve up like this, one of two things, as far as we're concerned in this particular class, is going on. Either it's an exponential or a power model. That's going to be our next two that we look at. An exponential model, you've dealt with exponential functions in classes before. That's when x goes up, we multiply y by something, like if you're doing compound interest or growth of a population. Very generally speaking, exponential problems look like, let's just call it a to the x power, where some number is getting multiplied over and over again every time x goes up one. Power models are x to the a, where our variable is the base of the exponent, and the power is a certain number. This would be like x squared versus 2 to the x. Exponential would be like 2 to the x. Power would be like x squared. Those are just general examples. And certain real-life scenarios fit into each one. You know, if your bank account's growing, that's exponential. Like this example where we're doing length versus mass, that's going to be more like power. And if you're just looking at a set of data, most of the time they're going to curve up in this general pattern. it's hard to tell which one it is. You could guess from the context about the lengths and the masses, but if you just see some curved data, you don't know which one's going to fit first or fit better. So here are the rules for each. In exponential, the opposite of exponentiation is logarithms. So in order to straighten out the curvy graph, if it's exponential, what we need to do is we need to take the log of y. If we graph x versus the log of y, then this curvy pattern, you know, if you remember what a log graph looks like, a log graph kind of looks like this, which is the inverse of exponentiation. If you sort of merge those two things together, what we end up with is a straight line, and that's what we want to have here. We want to have linear regression. So to make this happen, to check and see if exponential is best, what we're going to do is we're going to do log of y and graph that against x. So in my lists, 3 and 4 are x and y. In 5, I logged x, so I just went up to, clear it out so I can do it again. I went up to 5, L5. I hit log of L3, and so that programmed my list to take the log of all the numbers in 3 and put them into 5. So those are my log of x's. I'm not using that yet. My list 6 is the log of all my y values. So I did the same thing. I went up to L6. I typed in log of L4. So my 4 lists that I'm using, 3, 4, 5, and 6, are x, y, log x, and log y. The first one I want to do is I want to make a graph of x versus the log of y. So that's list 3 versus list 6. It's still a scatter plot. I need to change my zoom because my scale will be drastically different. And my other equation is still in there. Let me get rid of that. So here's my graph. And you can tell that it completely turned it around. It made it from arching upward to arching downward. It kind of turned it into what looks like a log graph. So maybe we can tell that this has kind of overdone the straightening out, but we'll see. So let's go back to Stat, Calc, and Reg, option 8, and let's do the linear regression and see how good of a straight line we have. So this is 3 versus 6, L3, comma, L6, comma, bars, y bars, function, y1, enter. So if I graph x versus log of y, you can see what happens. I overdid the correction, basically. Okay, so exponential is very steep. So if I undo that, I get kind of very unsteep, very arching downward, the way these dots are. My equation is, let's see, negative 0.038 plus 0.265 x. However, this, I should say, is the log of y, because in this variable, my original variables were x and y. Now my variables are x and log of y. So let me put that log of y in there. We'll talk about the math behind that in a minute. The correlation is 0.91. So this is even less linear than when we started. Our obviously curved data has gone from curving upward to curving downward, and a straight line is even worse now than when we began. So hopefully power, like we suspected to start out, is going to be better. So let's talk about how to do power. Power model is log x versus log y. Right, back in my lists, my log x and log y are list 5 and list 6. So let's start with making a graph of list 5 versus list 6. Let's just see what it looks like first. Zoom 9 always. And get rid of my other line again. So when I do zoom 9, I get a pretty straightened out set of data. All right, there's a lot of math going on behind the scenes here, and we're going to do a little bit of it. But for right now, either you're going to log y or you're going to log both, depending on which one. If you log y, it's called exponential. Both is called power. So this seems to be like it's going to be the best option. So let's do our linreg on 5 and 6. This 5, comma, this 6. Go ahead and put it in Y1. So you can see it got added over here, my graph screen. And a straight line seems to be very strong in this case. All right, so what are my values? My variables now second. My variables are log x and log y. So the log of y is equal to a is negative 0.136 and b is 3.139 times log x in this case. And that's my equation. The correlation is 0.9966. So this is obviously the best model because it has the strongest correlation. And just by judging from the picture, we can tell the first two were definitely curved. This one is good. It has a high correlation, and this is the model that's going to let us model this data and make predictions. If you had another animal's heart length, you could tell their heart mass from this particular model. All right, so last thing to discuss is what do we do once we determine that logging both variables gives us the best result? The typical follow-up question to which model is best would be, okay, what if we have an animal whose x value is 10? Well, what's y? The problem is you can't just take the a and the b that you just found in your power model, plug in 10 for x, and see what y is, because the variables are no longer x and y, they are log x and log y. We need to answer on the level of just x and y. So here's a little bit of the math behind the scenes. If you do an exponential transformation where you log only y, then your equation, the a and the b that you get, are based on y being now log y. So you get a plus b times x. And x is still x because we didn't log it. Now, if you'll remember from Algebra 2, in order to solve for a y that has been logged, raising it to where it's the exponent of a base of 10 is how you undo a log. So 10 to the log y equals y. And now this side is 10 to the a plus bx. So with the a and the b that the calculator gave you for exponential, if you want to plug in a given x value, what you're going to have to do is, on my right page, you're going to have to plug in your a and your b, your x value into that, and then you're just going to have to do 10 to whatever to get your answer, to make the long story short. Right? If you use your a and b that was given in exponential, plug in the x like you would, multiply it by b and add a, but then raise it, do 10 to that power. If both of them are logged, a little bit more complicated on the math, but not too bad. You start out with log of y equals a plus b times log of x. We're going to do 10 to both sides. 10 to the left equals 10 to the right. So now we're at y on the left. This side is 10 to the a plus b log x. All right, so now we've got some power rules, some log rules in effect here. 10 to the sum, a plus b log x, is a times 10 to the b log x. All right, and next step, 10 to the a, 10 to the b log x is 10 to the log x times 10 to the log x to the b, and 10 to the log x is just x. So long story short, I'm going to talk more about this when we have more time. Your model is going to be 10 to the a times x to the b. All right, so I need to cut this off before the 15-minute mark, but make sure you have that written down for power, that written down for exponential, and that you've got those calculator steps down in my lists. All right, so this is Young, and I'm out.